Okay, so these are the questions that have been emailed to you with prior advanced warning that these are in fact the questions that I am going to ask. We are going to use this polynomial 6x to the third minus 29x squared minus 6x plus 5 as our example of how to go about this whole process. So the first question that I have is question number 1, tell me how many roots there are. And this is basically the fundamental theorem of algebra. So, Smitty, my question is, based upon what you can see in this polynomial, how many roots would there be?
It would be 3.
Okay. And tell me why. The fundamental theorem of algebra says that the highest power is going to be equal to the number of roots.
Okay.
Okay. So if we're looking at this polynomial, what we're actually looking at for the highest power is this number right here. If the highest power is 3, there's going to be 3 roots. We don't know if they're real. We don't know if they're imaginary. We don't know if they're positive. We don't know if they're negative. Right now, just as it is, the fundamental theorem of algebra says there's going to be 3 roots because the highest power in this polynomial is 3. Okay, so now we get into Descartes' rule of signs will tell you the number of positive roots, negative roots, and complex roots, but you have to jump through some hoops first. So you said that basically you can tell by looking at the sign changes. So what I'm going to do is I'm going to write down just the coefficients. And we're dealing with this very first question, how many roots are positive? So I've got 6, then I've got negative 29, then I've got negative 6, and then I've got positive 5. Okay? So those are the coefficients. To find the number of positive roots, you're going to count the number of sign changes. So if the first number is a positive 6, that is 1 sign change. It goes from a positive 6 to a negative. Now, negative 29 does not change signs when it goes to negative 6. So that is not a sign change. However, going from negative 6 to positive 5, that is a sign change.
Yes.
So that means that there is going to be, according to Descartes' rule of signs, there is going to be 2 positive roots.
There was something confusing whenever I was watching the video because it was like you can, whenever you have like positive or negative roots or whatever, it was saying that you can have like 2 or 0 or something.
Okay, so we're gonna hit on that because there's fine print. Okay, there's fine print to Descartes' rule of signs. The fine print basically says if you can subtract 2 and not get a negative number, then there could be a possibility of other scenarios. So as far as the positive roots are concerned, that fine print would tell us that there could be 2 or there could be 0 positive roots. Okay? 2 or 0 positive roots. And the reason is because 2 minus 2 is equal to 0. That is the fine print that Descartes' rule of signs says. But now it also says that for the negative roots. Okay? So be aware that we've just answered this question and we've just answered this question. But the next question is how many roots are negative? The only way to tell how many roots are going to be negative, we are still working within Descartes' rule of signs. The only way to tell is to replace x with negative x.
Yep.
And then see what happens. That's the only way to tell. Now the shortcut is simply this, that if you replace x with negative x, the only signs that are going to be affected are going to be the odd-powered signs. So in other words, if I were to go in here and replace and make it 6 times negative x to the third power, and then this would be minus 29 times negative x squared, and then this would be minus 6 times negative x plus 5, okay? So just notice all I've done is replaced all the x's with negative x. That's all I've done. And then I'm going to simplify this. Well, this becomes a negative 6x to the third, whereas up here it was a positive. Now the negative 29 does not change. This is still going to be negative 29x squared, because negative x times negative x is positive x squared. So the even power did not change. See? It's still negative 29. Now, x to the 1, this is now a positive 6x. So that's an odd power, and it went from a positive 6, or it went from a negative 6 to a positive 6. And of course, the constant is not going to change. So now, if we are using Descartes' rule of signs, now we're going to look at the number of sign changes. Now we have negative 6, negative 29, positive 6, positive 5. How many sign changes are there?
1.
And where does it occur?
Between the negative 29 and the plus 6.
Perfect. There is 1 negative root. Are there any other possible scenarios? The fine print said if you can subtract 2 and still get a whole number, then there could be another scenario. So if you can subtract 2 and still get a positive number, or I should say positive or 0, and still get, really truthfully, the way we would describe that set is a whole number. If you can subtract 2 and still get a whole number, then there may be another possible scenario. Okay? So in this case, we know for sure that there is 1 negative root. For sure, for sure. We're not sure about the positive roots. We don't know if there's 2 or if there's 0. But we know absolutely beyond reasonable doubt there is 1 negative root. Okay? All right, now, how many complex roots? In order to be able to answer that question, you're going to want to set up a table, which is this question right here. It says, explain how to find different scenarios using a table. This is still part of Descartes' rule of signs. Okay? So when using a table, what did we learn absolutely for sure, for sure?
2 positive or 0, and then 1 negative root for sure.
Okay. So we know for sure that we have 1 negative. That is not going to change.
Yep.
But we have 2 or 0. Okay. So if there, and what's the total number of roots that we have?
3.
How do we know that? Fundamental theorem of algebra said that there were going to be 3 total roots. That's this 3 right here, circled in red now. So we know for sure now there are 3. So there are a total of 3. Let's just say if there were 2 positives and 1 negative, how many complex roots would there be? There were 2 positives and 1 negative. How many complex would there be, knowing that there is a total of 3? 2 plus 1 plus 0 equals 3.
Yep.
So then over here,
on the other side.
that's right. 0 positives plus 1 negative. We've got to have 2 complex roots for a total of 3. So in other words, we've got 2 scenarios here. And at this point, we don't know which one of these 2 scenarios it is. We don't know if it's going to be 2, then 1, then no complex, or if there's going to be no positive roots, 1 negative root, and 2 complex roots. But we do know that there has to be a total of 3, and we also know that complex roots always come in pairs. Okay? So you will never have an odd number of complex roots. They come in conjugate pairs. Okay? So if one of your roots was 2 plus 4i, then the other root would be 2 minus 4i. Complex roots always come in pairs. Okay. So now that's kind of confusing, being able to use a table in order to explain all of the different scenarios. Okay? And so we're going to keep going, and we're actually going to figure out which one of these two scenarios it is. But at this point, we're jumping down to the rational root theorem. This is where you're going to do your plus or minus p over your plus or minus q. All of the factors of p over all the factors of q.
Okay.
So what are the factors of p?
5 and 1.
Okay. So 1 and 5, and of course that's plus and minus for both of those. What are the factors of q?
1, 2, 3, and 6.
Okay. 1, 2, 3, and 6, and of course that's plus or minus. So when I ask you to list out all possible rational roots, okay, all possible rational roots, what would they be? What are all the different combinations of p over q?
5 over 2, 5 over 3, 5 over 6.
1, 5 over 2, 5 over 3, 5 over 6. Okay. Are there any others?
1 over 2.
Okay. So these were your answers. I have to be methodical about it when I list them. Okay? So I go 1 over 1, 1 over 2, 1 over 3, 1 over 6. Then I go 5 over 1, 5 over 2, 5 over 3, 5 over 6.
And then all those are pretty much just going to be swapped upside down.
That's correct. But what I actually have written down right here is actually only half of them. So that's why I put a plus and a minus in front of this. Plus and minus. Okay? So plus and minus 1. Plus and minus 1/2. Plus and minus, etc. Okay? Okay. So these are all possible rational roots. That does not mean that any of them will actually work. And quite obviously, all of them could not possibly work because there is a maximum of how many roots?
3.
3. There's a maximum of 3. Okay? According to our table here and Descartes' rule of signs, 2 of them could be positive, 1 of them could be negative. Or none of them could be positive and 1 of them could be negative. So that means that of these, 1 of them could be negative. And we're going to use one of the roots, and we're going to perform synthetic. There's only 2 roots, really. Well, I guess there's 4 on there that I would even be interested in trying to test out, because I really don't like to do rational root with fractions. It can be done. It's just nobody really likes to work with fractions. 1, 1, negative 1, positive 5, negative 5, and that's it. P is always going to be the last number. Q is always going to be the first number.
Okay.
So it's always the last number, factors of the last number over the factors of the first number.
Okay.
That's always the way it's going to be. Plus and minus factors of the last number over factors of the first number. To me, how to set up synthetic division.
You just put the equation in right there, like in that space.
Not the whole equation, no.
No, just the numbers. 6, negative 29, negative 6, and 5.
Okay. So 6, negative 29, negative 6, 5. So we're going to go 6, negative 29, negative 6, 5.
Drop down the 6.
Okay.
And then 1 times 6 is 6, so put that at, yep, negative 29 plus 6 is 23, yeah, negative 23.
Is that right? Negative 23,
right.
yeah. It's 1 times 6 is 6, add down.
Yep.
Then 1 times negative 23.
Negative 23, so it goes back to negative 29. And then negative 29 plus 5 is negative 24.
Okay. So we got a remainder here.
Yep.
Okay. So because we got a remainder, that means that 1 is not a root.
Nope, because it has to be a 0.
That means that 1 is not a root. So let's test negative 1. Since 1 did not work, let's now test negative 1. Okay, so we started out by testing 1, and we got a remainder of negative 24. So then we said we were going to test negative 1, and we both did it on our own. He did it on his paper, I did it on mine to confirm negative 1 does not work either. Now when we say does not work, what that means is that we're always getting a remainder. It will work if you do not get a remainder, okay? So he tested negative 1, it did not work. He tested negative 5, it did not work. Now I'm going to show you that positive 5 does work. So it's really easy for me to just kind of delete all this stuff out of the way. So I'm just going to delete all this stuff out of the way. And then if I put in down here a positive 5, then 5 times 6 is 30, add down. 1 times 5 is 5, add down. 5 times negative 1 is negative 5. Hooray, we get a 0. This is what we wanted. We wanted to have a remainder of 0. I don't know what the remainder was for positive 1, or I'm sorry, I don't know what the remainder was for negative 1 or for negative 5.
For negative 5, it was negative 1,440, and for negative 1, it was negative 24.
Okay. So I'm going to assume that all your math was correct on that, and that those were the remainders, and that's what prevented this from working. However, fortunately, we found one of the roots, which was 5.
Good.
Okay. So this is really, really important, and a lot of people get this screwed up. If 5 is a root, then x minus 5 is a factor.
Yep.
A lot of people get that wrong. Okay? There's a difference between a root and a factor. All right? And the reason that we know 5 is a root is because we got a remainder of 0. It divided evenly. Okay? It synthetically divided evenly, so we got no remainder. And when we're dividing, we like to get no remainder because that means that we've divided evenly. So that means that we now know that x minus 5 is a factor of that original polynomial, which back over here, the very beginning, this was the original polynomial, and right down here, for this question, it says, tell the difference between the root and the factor. Well, 5 was a factor, x minus 5, I'm sorry, 5 was a root, x minus 5 is a factor.
Gotcha.
Okay. Then it says, provide the depressed equation. The depressed equation comes from your quotient. This.
There's 6(1) minus 1.
This is the depressed equation. Yeah, the remainder theorem says that if you synthetically divide and you get a remainder of 0, then the number that you divided by, which was 5, is a root. So tell me what the depressed equation is.
6x squared, hold on a second, plus 1 minus 1. No, plus 1x minus 1.
Minus 1, right. And so you're like, how did you know that? Well, this was 6x to the third, this was x squared, this was x, and this was our constant. So the depressed equation is always reduced by 1. Okay? So that's how we ended up getting the depressed equation. Okay. Now we could, if we wanted to, and it might be easy to do, I don't know, but we could take this depressed equation and try to factor it. So 6x squared minus 1x minus 1, was that what it was?
Yes.
Plus 1x. Plus 1x.
Yeah.
Okay, now I don't know if this thing factors nicely. I'm just going to try a couple of different choices here and see if it does. That would be 3 and 2, positive, negative, yes. So it does factor nicely, okay? So this was our depressed equation, and I took the depressed equation and I factored it.
And then you
In fact,
flip
some
this
of you
on.
would have done factor by grouping, but I can just do factoring really easily like this. And if you need to see to confirm that this thing right here factors into this, that would, if I were to FOIL it, it'd be 6x squared plus 3x minus 2x minus 1. So that would be 6x squared plus 1x minus 1. Okay. So I do know that these are 2 other factors. Okay. Now the problem did not ask us to find all of the factors. Okay. It did not ask us to find all of the factors. It said use one of the roots to find the depressed equation, and we did, using synthetic division. And then it says describe how the remainder theorem applies to your example, because the root that we picked, which was 5, and we tested it, we got a remainder of 0, that meant that x minus 5 was a factor. So actually, I can list out now all of the factors. X minus 5, 3x minus 1, and 2x plus 1. These are all of the factors. If I were to multiply all of these factors together, I would end up with that original problem, which was 6x to the third minus 29x squared minus 5x minus 5, I believe, is what it was. If I'm not mistaken. Yes. Okay? So these are all the factors. 5 is a root. X minus 5 is a factor. What's another root? 1/3 is a root. 3x minus 1 is a factor. What's the last root?
1/2.
That's right.
-1/2.
Negative 1/2. Negative 1/2 is a root. So according to this table, there was 1 negative root and 2 positive roots. This is your negative root right here. There is 1 negative root, and this is your positive roots. These are your 2 positive roots. 5 is a positive root, 1/3 is a positive root, -1/2 is the negative root. So in other words, back here on this table of values, this is the total, this is the scenario that we actually had. Okay, let's finish up these questions. Let's talk about the end behavior. Tell me about your end behavior. You have 4 choices. Okay, these are your choices. You have up, up, down, down, up, down, or down, up. These are your 4 choices. You've got to pick one of these 4 choices.
How would up down look? Just like literally like a hill?
Good question. How does up down look? Up down looks like this.
It'd be down up.
Okay. Down up looks like this.
Yeah, that's how it would look, because that's what's greater than 0.
Up up looks like this.
No.
Down down looks like this.
No.
Okay. All right. So you're saying it's down up?
Yes.
Okay. How do you know? By just looking at the first term. How do you know?
Because if A is greater than 0, then that's what the equation is.
Okay. So the A was 6. Although when it's cubic, we don't really call it A. We just say the leading coefficient. Okay. So I'm gonna correct that. The leading coefficient was 6, and then the highest power was 3. So this is leading coefficient 6 means it's positive. Highest power is 3 means it's odd. Okay. So this situation down here is odd, positive. This one over here is odd, negative. This one over here, even, negative. This one over here would be even, positive. So can you give me an example of what the first term would be if it was an up-up?
6x to the 4th.
Perfect. What if it was down-down?
Negative 6x to the 4th.
Okay. What if it was up-down?
So it'd be negative 6x cubed.
Negative 6x to the
I was
3rd.
thinking the actual number being odd.
The highest power is what you're concerned about, whether it's odd. And the leading coefficient is just positive. And then this one over here, this is positive 6x to the 3rd. Okay? So these are all the different end behaviors that are possible. Okay? LC stands for leading coefficient. HP is highest power. Okay, last question is find the y-intercept. The y-intercept is always when x is equal to 0. So if you were to take this polynomial and plug in x equals 0 for the y-intercept, what would you get?
So are we trying to find y or are we trying to find x?
Well, okay, the y-intercept is whenever x is equal to 0.
Yeah.
So we're going to go in here and plug in a 0 in each one of these x locations.
And we're going to find the y.
And we're going to figure out what y is. So if you put a 0 right here,
it just goes away.
6 times 0. If you put a 0 right here, what happens?
Same thing. It's going to end up with positive 5.
There you go. Okay. So the y-intercept is 0, 5. The y-intercept 0, 5. The final thing, and this is really going above and beyond what the DBA is, but in order for you to have a full and complete understanding, the roots were, so these were the 3 roots that we got, okay? Here they are. Here's your 5, here's your positive 1/3, here's your negative 1/2, and then we figured out that the y-intercept was positive 5. That's actually right here, 0, 5. Because this number right here is 100, so you can see they're being ticked off by, what is that, 20, 40, 60, 80. Yeah, they're being ticked off by 20s. So that makes sense. But in order for us to be able to see the whole thing, and then you can see that it was down on the left and up on the right, okay? And then that also makes sense because our Descartes' rule of signs said that we were going to have 2 positives and 1 negative and 0 complex roots. And there were no complex roots here. Complex roots do not show up on a graph, okay? So we've gone through the whole process from beginning to end, and I think that this kind of gives you a good idea. We even went a little bit further here on this factoring problem and found all of the roots. For the DBA, you do not have to find all of the roots. You just have to test one of the roots until you are able to find the depressed equation. So you're going to be going through this process until you find the depressed equation. Please do remember that if you are testing a positive 5 root, then your factor would be x minus 5, okay? So it's kind of like the backwards. The reason for that is x minus 5 equals 0, therefore x is equal to 5. So that's the thought process behind that. Rational root theorem, Descartes' rule of signs using the table, fundamental theorem of algebra, that right there would be a complete 100%. When it comes time for you to do your DBA, I will ask you these exact same questions, except I am going to give you a different polynomial. And that will be a different polynomial for each student. So I hope that this helps you with your DBA.